Oh, hello, everyone. Thanks for joining this session. Okay, so today, as said in the topic, that we will spend the whole webinar just talk about the thresholding and the segmentation. So basically, these two words meaning the same thing. Basically, that's when you get a digital image, which means you have a 2D matrix with each coordinate has a value, which is your intensity value, and you want to somehow use a method to separate those pixels into different groups. In most cases, will be two groups. One will be your object group, one will be the background group. The object group will be the signals which you're interested, and once you create this separation, that you will get what we call the mask image, which are the pixels divided into two groups. The white pixels normally we consider where the signal is, and the black pixel is the background. And then we can use the software very easily to get outline of all the white objects. That's what we call the region of interest. Then you apply this region of interest to your raw image, then you can create all the measurements you will need. And as we mentioned in the previous webinars, the thresholding is basically the centerpiece of our digital image analysis, not just for the ImageJ. Okay? Any other image analysis software, by the end, your analysis successful or not, basically fall on the how good you can do the thresholding. So today we're just using more examples, just talk about how to achieve this goal. So you should have that, you should receive the email to download the material for this. And if you register within 24 hours, that you can also go to this website. And I also have the Dropbox links for the material for today's, that you can download. The link you can find in our training resource site on our core. So we'll first start it. Let's say you will have the FIJI ImageJ started. So I will first go to the folder A, the fixed value thresholding. So this is the image I used in the previous webinar. You open this. So this is what they call the fixed cell. It's not really a cell, but we consider those are the cells. It's the cell, the white object are the cells. So I magnify this more. So our goal for the thresholding is we know that when we identify the cell, our criteria will be the cell should have a strong intensity, especially if you're doing the fluorescence. So the background is black and the cell is more white. So if you use those line function, I can draw lines through here and I go to analyze plot profile. We can actually get to the line profile through the straight line you draw. So you will see the first part with where the background is, the intensity is about below 100, about 70, 60. And once you go into this cell, you can see the intensity goes up. Then we leave the cell, the intensity goes down, goes up again. So by here, we can get a feeling that the cell intensity is kind of pretty high, about 100, 150. The background is around like a 70, 80, getting? So something around here, maybe 100. We'll say all the pixels with the intensity higher than 100, we consider it as cell. All the pixels with the intensity lower than 100, we consider as background. Probably we can get a pretty nice representation in this whole image, what the cell looks like. So I will close this one. So I will do the thresholding. So the thresholding, the function in the ImageJ is in the image, adjust, threshold. And I said, this is basically the fundamental piece of all digital image analysis. You're going to use it all the time. It's the image adjust threshold. So I will suggest you check the dark background for this image. Also in this option, you choose red. So basically you will see there's two slide bars here. The lower one shows the higher threshold. In this case, I will keep it as the highest value is 255, because we know that the cell, if it's the pixel belongs to a cell, it has a high intensity. And this is a lower thresholding value. So this is you can play around. So if I choose it here, you can see this 88. So what means that all the pixels with the intensity value higher or equals to 88 will showing up red here. So our goal is try to play around this to find one thresholding which the red object showing up just represents what we think is the best representation of our cell. As we said, we by the line, the profile we think the 100 may be good. And here I kind of change my idea. I think maybe 115 is good. So to show you the comparison, I also load the raw image here. So this is 115. So this is a raw image. This is it shows you what the thresholding image will be. So I think it's a good representation. So once I think it's good, I come here, I click apply. So this one becomes the thresholded image, which also we call the mask image, or also binary image, because in this image, it only has two kind of pixels. They're either black pixels with the intensity is 0, or the white pixels with the intensity is 255. If you can get a very nice mask image, represent what your object, what your region of interest is, then if you want to get the selection of your object, will be very easy, as we described in the previous the webinars. Once you have a mask image, you can do a analyze particles. So basically you can tell it, I want to analyze all the objects. We want to add it to the ROI manager, and we also don't want anything on the edge, which I want only the whole object, and it will create this region of interest very fast, very precise, and you can show it up here. You can zoom in. So you can see actually it draws a very nice outline for you. And then you can make all the necessary measurements on this. So our goal is always, when you look at the image, you try to play around and to know what's the character of your image. Then you find a way, either in the thresholding by the intensity value, or you can do something before to make the image easier to be thresholded. And you can give you a very nice mask binary image, which the white region represents what your interest is. And then you can use the analyze particles to gain those region of interest, then doing all the measurements back on your raw image. But then you will see all the measurements totally rely on how you did the thresholding. Why you choose that thresholding value. And then there will be get some kind of controversy on this. Like, what is the best threshold holding? So let's say, I'll close this, I'll reopen this one. I'm going to zoom into this cell. I will also drag this ROI. So this outline is if I use the thresholding as 90, getting? So all these pixels inside this selection with the intensity lower than higher or equal to 90. And I can also change the thresholding value to 100. You can see that it's getting smaller because there will be less pixel fit this criteria. I can keep going up the thresholding value from 90 to 130. Getting? And when you look at it, you will be able to see, you may have your preference, what will be the best to identify this cell. But when we look at this, we will say, at least for me, I will look at those, all the selections, I will say, they are all kinds of reasonable, getting? What I mean, the reasonable is kind of, I can kind of defend myself to say, when I select as this is the outline of my cell, I look at this image, I think that looks okay. And someone may think it's like too small. It should be more like this. For someone, we may agree with me. And it's not definitely wrong when you look at something that's definitely wrong. It looks like a reasonable representation of this cell. So why I choose 130 or 110 or 120, I have no reason to defend myself, like why I choose this value. The only thing I can say is I like it. This is my data. I know my data best. I know my cell the best, and I believe this is the best representation of the outline of this cell. Then I'm going to do my measurements based on this threshold holding. But as you can see, if you fill them out, you do the measurement. I do the measurement on the size and also the mean intensity. You will say through these 5 choices with the different threshold holding, the mean intensity changes about like go over 20, and that is almost like 7-8%. And also the size changes a lot. Getting? If you consider the smallest size with the thresholding 130 and the biggest size with thresholding 90, the size change is almost 50%. So if your goal in your research, your project, is to compare the size change of under 2 conditions, your control condition and your experimental condition, then which one to choose will be totally decided by the thresholding you choose. Like for example, I haven't do the measurement yet, but my hypothesis means the experimental one, the cell size will go bigger. That's what my hypothesis is. And that's have all I done this experiment. I spend the effort, the money, the time. I'm in the lab. I already have the paper almost in shape. I only need this result out to submit the paper. And then I know that if I actually choose the lower thresholding, they actually give me a bigger size. So when I actually looking at my experimental data, this cell, I may just intentionally, maybe not intentionally, maybe just in my subconscious, I feel, I hope so bad it will be bigger. And I know you want it to be bigger, only you need to do it to change to a lower thresholding. So I may just feel when I choose this thresholding here, I will feel this one will be a better representation than this one. Not exactly what I really feel. It's just maybe in my mind, I know this one will give me the result which I want, which I believe is true. Really? And it looks reasonable. I can totally defend it. Really? And the same thing when looking at the sample image from the control group, which by my hypothesis is that the control group, the cell should be smaller. Then when I try to select the threshold holding to identify the cell in the control group, I may more likely to choose the thresholding 120, 130. Because I know it will make it smaller, and I believe that is what's happening. Getting? And then you will see the problem here is I can give you the exactly same image by what you are feeling it should be doing. You can actually create a size difference with a 50% difference. That's a huge difference. Really? I believe in most cases, if you're doing the experiment, once you see the parameter you want to check between the control and the experiment, there's a 50% difference, you're very happy. That's definitely, we can write a paper on it. But this actually the same image. By just using different threshold holding the method on it. And the best thing is, actually, they all look reasonable. You can't really see anything wrong with it. Those are different choices. Yeah. So let's go back to our point. We said the thresholding is basically the centerpiece of all the digital analysis. How do we avoid our just the subject bias on this? Okay? When you're choosing on when you're first looking at an image, what thresholding to choose is totally by your decision. As I mentioned, it's my data. I understand it best. I choose the thresholding which I believe best represents this cell. But once you choose the value for this image, you choose the thresholding 110 or 130, then you lose the flexibility to change it. You have to use the same value applied to all the images in your control group. You should use the same thresholding on all the images in the experimental group. Getting? And only in that case, you will say, do I see a statistic difference between the size? You can also use 90, nothing wrong with that. But if you use 90 on one image, you should use the thresholding value 90 on all the images. Okay? So that's the important thing. It's always the consistent. You can always working on different image. Even here on different cell, you may find the different thresholding value represent what you consider best outline for the cell. But you cannot do that one on every single cell, just what we call the cherry picking. It's not important how good your result is on a single image, reflect what your subjective view on what the image tells us. The important thing is always if you can find a fixed value on the thresholding and actually fix the steps, the protocols on every single image, that we use the same step, same process, goes through all the images. Then we check out the result. If we see the statistic difference, significant difference between two groups, then we can be more confident. We can say that's a reliable the result. The cell size in the control group is bigger than the experimental group or lesser than the experiment group. In that case, it doesn't matter which thresholding you use. The important thing is you have to use the same value on all the image. So it's always try to find a value which can work on majority of your images, which yield a reasonable result. That is more, you should spend time on it. I never suggest people to spend much time to play on a single image, try to get what exactly the ideal result it is. It's always the consistent, especially on the fluorescence, those the confocal images. A single image doesn't mean anything. I always feel like this way. You have to get apply to multiple images to get the statistic to say if actually you see the difference is real or not. So this is one thing that's when you first to choose what thresholding is the best, it's purely your choice. Yeah, getting? But once you decide the value, you need to make sure that this value is used on all the images. That's the best scenario. But in reality, many times it's not that perfect. Yeah, getting? Sometimes you just don't have the luxury to use a single value thresholding applied to all your images. Getting? So in that case, actually, all this imaging analysis software getting provide a way to say you don't need to manually use the value to apply the value to it. They actually, the program, they have different algorithms to calculate what the value can be. They basically look at the image, they pick up all the pixel information, the histogram, they do some calculations, getting? Then they try to guess what will be the best thresholding to separate your pixels into two groups, getting? And the ImageJ provide you quite some functions to do this. So we'll go to the second one, the thresholding value by the algorithm. So we have quite some images here. We'll do that one by one. We'll go to the cell. So this is the cell. And let's say we go to the thresholding. So this part is you manually choose them. So we choose them around. Let's say what will be the best for the, so maybe about 44, I think 43. And also you have this portion. If you check on this, this gives you about, I think, 15, 17 that names. So this names is just the name of the algorithm they try to calculate this thresholding. So let's say if I choose this one. You click a triangle, it will give you what, by this method, it calculates the thresholding value should be used 15. It doesn't look that bad, but it seems a little bit low. So let's try something else. It's a default. So if you use a default, they will say by this method, they calculate as 64. So it may not be that good because you can see this cell is not closed. So we can't really use any kind of the binary function fill the holes to get the whole cell. So this is too big. So you can play around this. This is Huang and also this is just many of them just by the author's name, the OTSU. In this case, OTSU gives you the same as, you can also do the Yang. So in this case, what you can do is that instead of finding a specific value, you choose what algorithm you use to calculate it. So if you think, in this case, the OTSU, as I mentioned, is not good, I will use maybe, I think the Huang is good. So I will use the Huang, okay? So in this image, I give you the threshold is 26. When you have another image, you still use the Huang algorithm. It will calculate by the same principle, but the actual value will be different. In this case, we'll say, then someone may argue that you use a different value on different images. And supposedly it's not right. Yeah, it's not perfect. I would say it's not the ideal case. But in many cases, you have to do it in this way. We'll show you in the next exam. The next example. You just cannot afford to use a single value on all the images. In this case, when we do different image, we actually use different values. But we can still say that we treat all the images the same because we use the same algorithm to calculate it. we do not manually, just personally, very subjectively, to adjust the thresholding to fit our goal. It's not ideal as I use a single fixed number as a threshold, the thresholding, but we still use the same way to treat all the images the same. We're still doing our analysis in a consistent way. So if two groups of image, the measurement shows up the statistic difference, which are significant, we will still consider this is reliable result. Just not as good as if you can apply a single value to it. And you can play around those three methods. You will say, like for this one, okay, I goes to the, so this Huang seems also good. I mean, triangle normally give you a much less value of the threshold holding. This is yen getting. It's not that good. If you want to get the whole, the OTSU doesn't seem good. And these seems also okay. So you can play with your image. Once you have your image, when you do the image analysis, I would say the first thing is you just open some typical image, just play around like this. Okay? You need to know your image, to understand your image. Then you begin to can have an idea how to separate your image, signal, and the background. You get a feeling what's the character of your image. Then you found a way, like what is intensity value by some other method. You can separate the pixel in the signal region, your object from the background. Then you can do the thresholding to put them into two groups. And then you can make a mask image. You can just use to analyze the analyze the particles to get the outline. Okay? So those are the also for this this kind of I think some kind of Western plots the image, but since I will just invert it, so I work on the white, the strong. You can say it depends. This one give you those blobs. Seems the Huang gives you more blobs, and the triangle even gives you. So it depends on which you consider is more kind of the positive, those the blobs that you can choose which one fitted the best. And the advantage of using this method over the fixed value is sometimes you just cannot afford to use a single value on all your images. Because if you consider the control and the experiment, the sample are going through different process, get it? So they may just have a different background value. It's not something you can control. You can make sure in the acquisition part, I use all these same parameters to get the image. But just because the sample goes through the different treatments, getting your experiment one may just have a higher background than your control group. So let's say I go to the portion C. So if this is your the control sample, this is your experiment sample. As you can see, it's basically the same image. I just add some value to the experiment one. Okay? So if you're doing the thresholding, let's say first do the control one. I'm doing this about maybe I would say it's 93. I think this looks nice. And then I use the 93, I go to the experiment one. I highlight this one. Now I change it to 93. You will say this doesn't work. The background is too high. You use the same thresholding, that 93 will be too low. Getting? If you set the thresholding, which is the best for the experiment, right? Like 143. And then you go back to the control. You go to, this will be too high. Actually, don't get the right outline for the cell. Okay? So because that you cannot really control the condition of your sample, maybe under one condition, your sample just have a higher background. Just a single value thresholding doesn't work for all the images. By my experience, it's very rarely that users have actually images under different conditions go through the imaging process, they have the exactly same thresholding can work. But if it's just the background change, the thresholding method can actually work very good to compensate this. So let's say I go to the control. I say I try to use the OTSU. I think the OTSU may be good. Okay, let's say I think this is kind of a good the representation. Then I know that in this case it's 103. If I go to the experiment, let's say if you go to 103, as we say, it doesn't work. For experiment, this method is too low, 103. But if I say I don't use the value, I'm going to reuse the OTSU method. It works pretty well. Actually, give you basically the same thresholding as the control, which you will see here. It gives you the thresholding is 153. So I use the same algorithm called OTSU. On the control image, it gives me 103. On experimental, it calculates, which is 153. And just guess what? I create this experiment image just by add 50 to all the pixels in the control image. So actually it matches very nicely what our consideration, when we look at the thresholding, what we consider the best cell representation is. Even you add a background. Here I intentionally that I artificially add the background, but the algorithm, it can sense that the whole histogram just shifted. Here you can see the histogram here, and here, it just the whole thing shifted. If just the background shifted, that if you use the algorithm-based way to calculate the thresholding, it can compensate it very well. And that's actually, I think, the most of the time when we're doing the imaging analysis, we'll say we do not go through the fixed value. It's not just because it's not good or something, it's just it's not a practical way in majority of the cases. That requires all your image has the same staining condition, same acquisition condition. And in many cases, your control and the experiment one, you just cannot keep that the same, getting? So many times you can see the background change just by how they change the sample condition, and the staining somehow changes. But if you use the thresholding method, getting? You choose, rather than choose a fixed value, you choose the algorithm to calculate it. It can compensate this really well. I'm going to quit the screen a little bit. I'm just so if any questions in this. So it's one. You also ask when is the local adaptive threshold necessary. So that's what we'll talk in the next section. So again, our goal is when we're doing any analysis, our goal is to try to make our analysis process as objective as possible. Ready? We want to make sure we treat all the images the same. Then we believe our result is consistent and reliable. To do this, it requires we use the same, we treat the sample the same in a thresholding steps. Getting, as we said, this is the most important step when you're doing the imaging analysis. So to make this happen, if it's ideal case, what you can do is I use the same value, exact fixed value thresholding on all my images. Then I do the analysis. That's the best case. If you can achieve this, you definitely do it this way. But in reality, yes, it just, as far as what I met all the user, the images, this just doesn't work. You have to be able to adjust the thresholding value. And in this case, we'll say that if you use the algorithm-based one to calculate the thresholding works very well because it automatically compensates the background shift, the whole system, the whole histogram shift in your images. So I'm go back to share the screen. So I would suggest whenever you begin to analyze your data, you have your images, you just put into the ImageJ, go through the thresholding, you play around this, you play around the different method, just to get an idea which one fits it best, getting? And then later we really began to analysis, you have the idea what method you should choose or what thresholding value you should choose. Okay? The ImageJ give you the building, the thresholding, the method. You can also download any plugin if they use any other algorithm. So the next section is we'll just talk about a little bit how it calculates the thresholding. You may feel it's kind of the interesting, like how a program, an algorithm, know nothing about my image, because this algorithm doesn't care what your image is. It's a neural image, it's a Western blot, they don't care. They just take out the intensity distribution, then to calculate, like how it's calculated. So we will just use a simple example to show you how the OTSU, how this method, what kind of way they use to calculate the value for you, how it does to give you this 153 here. So again, all those thresholding method, you can find it in the ImageJ, in the document. They have those kind of the original paper, how they do that. So in this, the folder D actually have the original OTSU paper. You download that. So this is actually, so why it's called the OTSU is because that's the author's name. And as you can see, it's published in January 1979. That's 40 years ago. And I will say is that, especially in the computer science, those kind of algorithm thing, if a method developed 40 years ago, people are still using it now, it is very, very good. So it doesn't necessarily mean it will work for your sample, but it works on many, many kind of images. So I would suggest when you have your image, when you try the thresholding algorithm, definitely just to try this one. And if you go down, you will say that is how this paper looks like. That's all the thresholding method paper will look like. I guarantee you don't want to read it. I don't think I read it. I probably read it once, maybe 10 years ago, but I don't want to read any more. Really. That's the same of all the like mathematics papers and the books. I think that's one person mentioned that describe all the mathematics books is very like on the point. Like all the math books have two kinds. The first kind of the math book, you don't want to read it after 3 pages. And the second one, you don't want to read it after 3 lines. So if you want to read it very nice, you can just finish. how this done. But in our cases, good thing for us is we don't need to actually understand how it works. We only know some smart people figure it out. And what we only need to do is we try to see if it works for my sample. If it works, we'll just use it. So, and for this part, I would say how the OTSU works. So all the slides actually coming, I just download copy from the web page. It's just a very simple example, just give you a kind of the idea how this algorithm works. Yeah, so when you try to figure out some other algorithm, or in special case, you want to write your own algorithm, the method, you can get some insight from it. So the OTSU, what it works is you consider a simple example. If 6 times 6, total of 36 pixel images. The intensity value is from 0 to 5. We only have 6 possible the values. In real case, we normally, for 8-bit, we have 256 types of the intensity value. And this is the histogram. So we have 8 pixels with the intensity 0, 7 pixels with the intensity 6, 2 pixels with the intensity 2, 6 pixels with the intensity 3. So how it calculates the thresholding is that they first assuming any possible value as a threshold, the thresholding. In this case, 0, 1, 2, 3, 4, 5, 6 value. For every single value, they calculate one parameter. And then they compare all the parameters calculated throughout this possible threshold holding values. Then they choose one, what we consider will be best, the likely thresholding value. So for the OTSU, what we calculate is something like this. If we set thresholding as 2, ready? Let's say. So what we'll do is they separate all the pixels into 2 groups. Background with the intensity value, actually this is 3, the thresholding is 3. The background is all the pixels with value 0, 1, 2. And also the foreground, your signal is all the intensity with the 3, 4, 5. So for the background, they will calculate how many pixels, the percentage of the pixels among all the pixels. That's 8 plus divided by a total of 36 pixels. And they calculate the mean value of all the background. Okay? And they calculate the variance of all the pixels inside the background region. So standard for the background group, you get the mean and the variance. The foreground, you get the same, mean and the variance. And the parameter they actually calculate to compare will be this one. They call the within class variance. So it's the weight, the percentage of the pixels in the background times the variance of the background plus the percentage of the pixels in the foreground times the variance of the foreground. You get this value. This value is what you have if we are assuming the thresholding is 3. And you can do the same thing with assuming the thresholding is 0, 1, 2, 3, 4, 5. Then you put that everything in here. You calculate this final result. In OTSU, the standard is you compare all those values. The one gives you the smallest value is your thresholding. So basically, their idea is I found a thresholding value to divide this into 2 groups, and those 2 groups are very close to each other. That means this value is small. So basically, we try to find the thresholding value to divide all the pixels into background and the signal, and those 2 are very close. They are very similar to each other. In that case, we think we found the best separation. So this is how they do it. Ready? For the other algorithm, they may use the same kind of way. They also may use a totally different way to calculate, but you can always find the original paper that if you're interested into reading it. But I will just say, I just guarantee you probably won't like to read all these papers. And for us, it's very simple. Some people did this for us. Provide this tool. All we need to do is to check if this tool works for my sample. If it works for my sample, I would just use it. Okay? My goal, my job is just to make sure I use the same algorithm on all the images. Then we make sure that when we compare them, they are treated the same. So we are analyzing in a consistent way. If they show up the difference with the statistic significance, we will think it's a reliable result. Okay? So it's always the consistency is much more important than a good result in a single image, in a single data point. We just make sure we have a lot of images. You always need to make sure you have multiple images in each condition. You have to measure them, treat them the same way. Then you can see the result compare with the different group if they have the statistic significance. And the final part for today's talk, we'll talk about, some people ask what we call the local thresholding or the adaptive thresholding. So that is something, I go to example here. So this is something, if you set a single fixed value thresholding or use the algorithm to calculate, all they are in common is they use a single value to apply to the whole image. So you use algorithm, what all it does is calculate a value, what they think is the threshold value. Then they use this threshold value to apply to the whole image. That means the background level on your image is even. And this many times may not be the case. So if you go to the E, the local threshold one, you open the cell image. I will change this one to the file lookup table, so then you will see it more clearly. So this is the image. So apparently, the left side, the background is stronger than the right side. So if I say I go through the thresholding, if I found the lower thresholding, which will get a nice representation of the cell on the right side, then the left side is all gone. They're all over the thresholding value because the background is high. If you change this one, change it higher, if I say the left side becomes to a nice the representation of the cell, then the right side then is wrong. Some of the cell, they don't even identify it. Okay. So this problem you cannot fix by using a different algorithm, because no matter what you choose, it still calculates the thresholding applied to all the images. In here, what we need to do is we need to generate a thresholding depending on its local environment. So when we're doing the thresholding here, we want thresholding should be higher, and on this part, that should be lower. So this is what we call the local thresholding, or it's also named adaptive thresholding. So in this case, it needs you to design some kind of the algorithm will include the calculation of the neighboring pixels of the single pixel. So for every single pixel, it calculates a different thresholding value depending on its neighbors. So it will compensate those uneven background things. Here I want to emphasize this. For the image like this, it's most likely that something wrong in your acquisition. That means when you take the picture, the enumeration on your sample is not correct. It's not even. So to deal with this one, my suggestion is you should go back to your microscope, align the microscope to resolve this problem, to make sure the image you get is an even background image. And then only analyze the image under the right acquisition condition. Okay? Sometimes those uneven is not because of the microscope is not set up right, it's just because the sample itself provided. Then we'll try to use those local thresholding. But something like this is the most likely is your microscope setup is not right. In this case, to correct it in here is the last resort. It's the last resort, getting? You should first go back to your microscope to make sure your image is right. Because all the image analysis, the software, the ImageJ and any other ones, no matter how good it is, it's a processing. It's basically a processing machine. It follows the basic rules of any process machine, which is garbage in, garbage out. If your income image is not good, you cannot expect some process machine just suddenly give you a very good result. Even if it gives you the result, you should be very careful about it. Okay? You need to make sure every image you get is the best image you can get. Then you put into the ImageJ to analyze it. So let's say for this one, so all the local thresholding method is calculates pixel by pixel. Okay? So in the ImageJ, if you have the FIJI, you can do it as here, image, adjust, you go down. This is the auto local thresholding. So this is the method you can have. Ready? And this is the radius, as we said. All the local thresholding, the method for any given pixel, it will calculate the thresholding based on your neighbors. So here, just to tell you the program, how many neighbors you want to cover, how big of the range, basically the radius with the center of the pixel selected. What is the radius, the pixel you want to include in this calculation? And then it's a parameter 1, 2. So all this method, you can find it by this website. And you can go down to specifically like for which method, what it does, and what these parameters mean for. Some of them, the parameter 2 and 1 may not be even, or it's not even applicable. And what is the original paper and the main paper they use to apply this one in ImageJ. It's not much you can. I will normally suggest you just try them one by one. So I will give you an example is for this one, I will use this method called black. I'm going to use this one as a 75. I want to calculate kind of a big region to represent the slope, how fast this change through this. And the parameter 1, I will use minus 0.2. This one, I will use minus 20. And we are using white, the object. The background is lower intensity. Then I will apply it. So this is image. This is my mask. As you can see, this works much better than if you are single thresholding way. Here, I can do this one, looks much better here. But on the left side is, I don't get those settings. If we match the right side, then the left side doesn't really work. But if you use the local thresholding, it calculates based on your environment, try to guess what your background is. That works much better. Okay? So the similar things here, like for this is what's called the rise. If you directly use the threshold holding, you will say the lower part actually has a lower intensity value. So if you change the threshold in lower, you get a nice outline of the rise particles, then the upper side is too much pixel getting included. If you have increased one to get a nice image on the upper side, then the lower part don't have much. Yeah. So for this one, what I will do is I will going to use this one. Auto thresholding. In this case, I actually use the person. The thresh is one white object, radius 15. So you get a nice mask on this is the original image. It doesn't matter. This has a higher background. You try to guess what the background is. You should use. And also for this one, just a quick thresholding. For this one, I'm going to use the mean. This one also 75. Here I will uncheck this one because here our band is black. Our background is white, so I just uncheck this. So it's depending on. So the same one, if I change to another method, I use the OTSU, change this to 75. So this will be different. So basically, you can choose what kind of the method you use. It depending on how much you consider that background is. Then to give you what you consider which is bad. So in this case, if you use the mean, the method, they do not consider this one as a band. They consider this one the difference with the background is too small. It shouldn't consider as the object. If you use the OTSU, getting? But if you use your mean, the method mean, it will still consider it is, getting? So that will be depending on the different method, different parameter. Again, you choose one which works on most of your images, and you apply the same parameters on all those if the Western blot thing. I'm going to close this one, and I will see if any kind of the any questions on this. Can you apply the thresholding algorithm as a batch process? Yeah, you can. You need to know how to write the ImageJ macro or write it under the Python. As I mentioned in our previously, we hold the in-person 3-day workshop. We have the 1 day just dedicated on how to write the macro. But apparently, I think for the foreseeable, the future, we cannot hold any in-person workstation. And I don't think the online format will be a good way to do the macro. I plan to record some shorter videos put on our website, which is a series kind of focused on just the basic how to write the macros. I think I also mentioned last time, I plan to post it before the Christmas, so you can just come back to check on our website from time to time. You may be able to see some of the videos show up. Let's see about the question, Kelly. For the if your image is noisy, let's say that's also when you go to the thresholding, it gives you some very just a single pixel that's the white, as kind of the white object, really. In that case, the best way to do is on your acquisition side. I think you should take more time to do the average on it. Okay, so just to make sure your image is as good as it can be when you input into the ImageJ. And if somehow you already get the image, so one thing you can do is, let's say for this image, I will show that in the file. Well, if I directly do the threshold, holding, sometimes you can see like this part is kind of some kind of a noisy level that shows up. Yes. You can do some smoothing on the image on the algorithm side, on the digital image side, which is the process filters. So basically 3 filters you can use: Gaussian, blur, medium, and mean. You can use in the Gaussian blur, and you can choose what kind of the radius you can use. If I put it too much, you can see I smooth it all the way up. If I put it too small value, sometimes it doesn't really work. So you can see I will take the radius 2 pixels, then you try to smooth it out with your neighboring pixel. But in this case, you lose your resolution. You basically blurry this image. But then when you do the threshold holding, you will see that a single pixel shows up much less. You can also try use the different just filters. Gaussian blur, medium, and mean. Try to use the difference, the radius, the parameters go through that. And another one you can try is for those the uneven things. You can use what we call the rolling ball the subtract background. So it's in the process, subtract the background, and you put a rolling ball radius here, and you can see that if we click preview. So it's basically the same. The cut off the background based on the local estimation. In another sense, it works almost the same if you're doing the local threshold holding. So many times it works very similarly. Like this one, I click OK, and then I can just use a single thresholding to achieve kind of a nice. So the same thing, we can do it in the, like for the rice thing. If I change this, you will say, like here is kind of too much background show up. So I can first do a subtract the background. In this case, 50 seems okay. Then I change it. Then I can, the background is put it even. Then I can use the single thresholding. So many times you can try both approach, either with the local thresholding or the rolling ball, those the background stuff, just the background stuff, the subtraction. In a sense that if you use the local the thresholding, you actually have more parameters to play around to get it. In the if you use the rolling ball, the only thing you have is the rolling ball radius. Getting, but you can try both. In the auto local threshold in the parameter 1 and 2, you just have to check this web page. I think I put that in the slide. So if you go to the contrast, it will tell you what is parameter 1 is. Parameter 2 is not used. It's what is the mean setting. So what is your formula to decide what is background object and what is product. So parameter 1 and 2 are different for every single method you use. Okay? And you just need to practice on it. So many times not you think about which value will be good. You just try on different values just to see which value works the best. I mean, they subtract the background and the Gaussian blur. You can use them both together to reduce the background noise. But again, to reduce the noise, the best way is when you take the picture, you take a better picture with a picture with less noise. Any noise deduction in the digital image side always blurred your image, which reduce the resolution on your image. If you can get a crystal image with no noise level, that will be the best. So it's always when you try, if you see anything problem on your image analysis, your first way is to think is not how do I, on the image analysis part to improve it, is how I can get a better image. Then I can put into the ImageJ, and then it makes much less. Actually, I think it works much better. It saves you a much less. If you save you much kind of all the trouble in the future on the imaging analysis. So always when you're working on an image, if something wrong, you think give you trouble on the imaging analysis, the first thing to think is how can I do better on the imaging on the imaging acquisition on the microscope side? How can I get a better image, much nicer, less noisy image to input into the ImageJ? Yeah, getting. So that's actually I think it's very important, and I also think it's very important. Your image analysis and your image acquisition should start at the same time. So when you analyze your image, you realize something may be wrong with your image. That helps you to optimize your image acquisition process. Then to help you to get a better image to analyze. Then by the end, you get a much more reliable, better result. Yeah, no matter what kind of a thresholding method, you go to the Gaussian blur or any kind of smoothing method, you use the subtract the background. You can do whatever you want, you think is the best to help you to identify, to create a mask image. But you just have to remember, you have, once you decide all the steps, you have to apply the same steps to all the images. Just all the goal we have to do is we do all the steps, all the effort to make a good mask. But the most important thing is we have to make sure all our effort is consistent on all the images. So you have to do on every single incoming image, we have to go through the same process. Getting? And that's, if you learn how to write the macro language, that will be much more easier. But if not, it's if you just have to manually do them one by one, just make sure you write down all your imaging protocol steps. Just make sure all the images come in, they are treated the same. Only under this condition, we can trust when we get to the result, we can confidently compare this result with another result. Getting? I always think that would be more important thing. So I think already over our time, and thanks again for joining the webinar. And as I mentioned, that we'll begin to make smaller, shorter videos on our website on both the macro language. That's something I think many people are interested in, also on the basic imaging analysis. That if you can just from time to time check out, of course, the website, you may have found it, and also. If you have any questions, that you're also welcome to send me some of the sample images with a brief description of what you want to do. I cannot guarantee I can solve your problem. I have to say that probably 50% of the time when the user send me the image, I can't really fix that to solve what they want. We can do, sometimes we can, for some extent, we can provide the solution, but I'm always I'm always happy to help. Getting? So, okay, so again, thanks for coming, and just keep in mind just for our future webinars and any kind of video on our core website. Okay, thanks. Bye.